Hello, everyone. Originally, I was supposed to go get my student card at the university, but the problem is, as everyone knows in Hong Kong, currently there's a typhoon going on, and all the public transports are inactive and all the offices are closed. So I decided to do this video on black holes, and we're continuing our discussion on charged black holes and the Reissner-Nordström metric. And a minor disclaimer that I want to talk about before I actually go into the lecture is that most of the diagrams here have been drawn by Professor Rial and have been obtained from his lecture notes from his course at Cambridge, aptly named Black Holes. The reason for this is because Kruskal diagrams and Penrose diagrams for these kinds of black holes are a little more complicated, and it'll take a lot of time to draw myself in LaTeX. So I decided just to, for simplicity, just to obtain some of the notes from there. But I will cite my sources. In this lecture, I will talk about maximally extending the Reissner-Nordström metric, and I will kind of explain what we are doing. But essentially, we are doing the same thing that we did with Schwarzschild. We move on from Eddington-Finkelstein, and we see what the shortcomings are of that kind of coordinate system and how we can improve upon this coordinate system and maximally extend the solution of the black hole. So as always, I will outline what I will talk about in this lecture. First, I will summarize what we did in the last lecture. Then I will talk about the problems with the standard null coordinates that we were using. Afterwards, I will talk about Kruskal-Szekeres coordinates, and we've done this before in Schwarzschild, but I'll show you how to do it in Reissner-Nordström because there are slight differences, but the principle is somewhat similar. Then I will show you how to draw Kruskal diagrams and subsequently Penrose-Carter diagrams, and afterwards I will give a brief discussion on Cauchy horizons. So recall, in the last lecture, we wrote the Reissner-Nordström metric, which is shown in equation 1.1 in null coordinates. Basically, what we did is we introduced a retarded time and an advanced time, and where f is this function, where r plus and r minus r represent the inner and outer horizons. And from this, by suppressing the angular coordinates and setting the s squared to 0, which is essentially the definition of a null geodesic, we can obtain the radial null geodesics. And from this, we are able to draw Finkelstein diagrams to learn about the causal structure of Reissner-Nordström geometry. And we drew a diagram that looks something like this. This is the Finkelstein diagram with plotting both u and v equals constant, and we can see the structure of the light cones. Basically, if we follow the light cones from one way, we see ingoing light cones, and if we follow from the other way, we see outgoing light cones. And if you're not familiar with this, go back to the lecture before, and you will see this will be a little bit more clear to you. Now I will talk about the problem with null coordinates. The problem with null coordinates is very similar to that of the Schwarzschild case. In null coordinates, basically what happens is we can see there are some caveats, because as we derived in the last lecture, this function, if we inspect it a little bit deeper, we can see that at r equals r plus and r equals r minus, the logarithm diverges, because the natural logarithm is not defined for r, basically when the argument is less than or equal to 0. So we have shown that these two we have shown in maybe 2 lectures back that these two are coordinate singularities. So in principle, there should be nothing unphysical about them. Additionally, we see that there are 2 different solutions for the radial null geodesics, namely one for outgoing light rays and one for ingoing light rays. So therefore, by maximally extending the solution, we would like to find a connection between the 2 and summarize them into one diagram. So let us introduce Kruskal-Szekeres coordinates, and we have done this in a couple lectures back in the Schwarzschild case, and the trick is essentially the same. So basically, for the Schwarzschild case, we just exponentiate u and v to get rid of the singularities in the logarithm, and we do the same here. But there are some subtleties. So we introduce actually four new coordinates, u plus and minus and v plus and minus, and they are defined by the following equations. And what happens is this kappa plus or minus is defined by either the ingoing or outgoing radius minus either the outgoing or ingoing radius. Either the outer radii or the inner radii minus the inner radii or the outer radii divided by either the outer radii or the inner radii squared. And here we have four new coordinates, u plus or minus and v plus or minus, and these represent the coordinates near r plus and minus respectively. Then the Reissner-Nordström metric can be written as follows. And this derivation is quite long, but you can actually do it. I've shown how to do it in the Schwarzschild case, and it's essentially the same here. Here, to save writing, I wrote omega 2 squared as the angular coordinates on 2 sphere to summarize to save writing. But the r coordinate is defined implicitly by u plus or minus and v plus or minus in the following manner. And to examine the behavior of the null geodesics, similar to before, we can suppress the angular coordinates and set ds squared to 0. And for pedagogical purposes, let us plot the function f plus or minus versus r on a graph. And the lesson here is to understand the behavior of this function and see how the null geodesics changes with r. Now recall, the reason why this works is because Kruskal-Szekeres coordinates are conformal transformations of the standard Reissner-Nordström coordinates, and null geodesics remain invariant under coordinate transformation. But recall that a conformally related metric is not necessarily a solution to the Einstein equations, even if the original metric is a solution to the Einstein equations, because what happens is you will take derivatives and the conformal factor may be dependent on time or space, and this may or may not be the solution to the Einstein equations. You will see this when you have seen this before when I talked about Penrose-Carter diagrams in previous lectures, so just refer back to that. So looking at the behavior of the function, so the blue line represents the product u plus and v plus, and the yellow line represents the product u minus and v minus. And you can see what happens is that the u minus v minus coordinates is a monotonically increasing function here, but the u plus and v plus coordinates are a monotonically decreasing function at the point. Well, the red lines represent the inner, so the one closer to the axis, the y-axis is r equals r minus, and this one is r equals r plus. So u plus multiplied by v plus is a monotonically decreasing function beyond r equals r minus. And we can see from the graph that, as I mentioned before, u plus and v plus is a monotonically decreasing function in the region r greater than r minus. And we can see here in this region, or going back to the graph here, in this region between r minus and r plus, the product u plus and v plus is greater than 0. Which means that either u plus and v plus are simultaneously positive, or u plus and v plus are simultaneously negative to yield this solution. Conversely, notice that in the region r greater than r plus, we can see that u plus times v plus is less than or equal to 0, which means that in this region, either they have opposite signs, basically. So if u plus is positive, then v plus will be negative. And if v plus is positive, then u plus will be negative. However, as I mentioned before, notice that there is a vertical asymptote at, excuse me, give me 1 second. Notice that there is a vertical asymptote at r equals r minus for u plus and v plus. So what happens is u plus and v plus is not defined for the region between 0 and r between 0 and r equals r minus. And for that, we need to use a different set of coordinates, namely the u minus and v minus coordinates. And by using the u minus and v minus coordinates, we can extend the coordinates to the region r between 0 and r minus. And we can see that in this region, as looking at the graph before, this is a monotonically increasing function. And what you can think of is that the u minus and v minus coordinates are the analytic continuation of the u plus and v plus coordinates in the region where the u plus and v plus coordinates are not defined. So I've shown you how to draw Kruskal diagrams before, and essentially this is the same in Reissner-Nordström space-time. But what you can notice in this graph, we can see this is for the u plus and v plus coordinates. So the r plus region is defined by, as mentioned before, right? This is a graph depicting where the r plus region is. So we can see that when v plus is positive and u plus is positive, then we have this region r plus. And so basically these lines actually represent the r plus axis, and these regions represent the tell you the sign whether r plus is positive or negative. And I will note that I got this figure from Rial's lecture notes on black holes, and you can find this on page 88. So similar to the Kruskal diagram in Schwarzschild spacetime, the null hypersurface, basically a null hypersurface, I didn't explain what this word is before. A null hypersurface is a surface where all the normal vectors on this surface is a null geodesic. So what basically it is null, right? So what happens is u plus and v plus equals 0 intersect at 0, 0. And u plus is a null hypersurface and v plus is a hypersurface. So this is also a point in the hypersurface. So this can be thought of as a bifurcation of a two-sphere, and maybe I will explain that later when I talk about bifurcations in my lecture on nonlinear dynamics and chaos theory. But in this case, just another way to think of it for those who are more mathematically advanced, it can be thought of as a bifurcation two-sphere, where the killing vector is psi I equals 0. So for any surface of constant t, the lines are simply straight lines that cross the origin. So you can see here t equals constant is a dotted straight line that crosses the origin. And this is exactly the same as the Schwarzschild case that I showed before. And which means that there are Einstein-Rosen bridges that connect the two space-like regions, region 1 and region 4. So this line, you can see, right? There are no lines that connect region 1 and 4 except this t equals constant region. So since these are space-like separated regions, we can connect them through a line of constant t. So however, notice that in the u plus and v plus coordinates, there is no curvature singularity at r equals 0, represented by a hyperbola in the regions 2 and 3. This is very similar to, this is not at all similar to the Schwarzschild case, where there are two hyperbolas. You may remember there are two hyperbolas here for r equals 0. I think when I drew it in the upper region, but it doesn't really matter. It depends how you define your axes. For Rial's lecture notes, he draws it on the sides. So in this case, there are, recall that lines of constant r, remember here, lines of constant r are represented by hyperbolas. And we do not see the hyperbola r equals 0 on the graph. And this is because, as mentioned before, in the u plus and v plus coordinates, if you look at this graph here, in the u plus and v plus coordinates, it is not defined in the region between r minus and 0, right? So basically, we know from the standard null coordinates that the radial null geodesics will approach r equals r minus at some finite affine parameter. So therefore, u plus and v plus must approach, so the product must approach infinity at the same affine parameter. So we need to see what happens here. So let us change to the u minus and v minus coordinates, and we will see something very, very similar to that of the Schwarzschild case. We can see that in this figure here, that there are the characteristics of the Schwarzschild case, where there are lines of, well, the lines of constant t are represented by straight lines that cross the origin. Lines of constant r are represented by hyperbolas. And we can see that since in the u minus and v minus coordinates, they do encompass the region between 0, r equals 0, and r equals r minus. And therefore, we have the hyperbolas at r equals 0. So using the u minus and v minus coordinates, we have two space-like asymptotically flat regions, namely region 5 and region 6. So since these coordinates contain the regions basically between the inner horizon and the curvature singularity, we can see the curvature singularity at r equals 0, or the product of u minus and v minus equals -1, are represented by hyperbolas like in the Schwarzschild metric. But since these singularities are in the region v minus is greater than 0 and u minus is less than 0, and vice versa, these are called time-like curvature singularities because these are in the time-like regions instead of the space-like ones. So, so this is called a time-like curvature singularity. And notice that there is a region labeled 3 prime. This is a space-like region that is isometric to the space-like region in our region 3. So this 3 prime is labeled this way because it is isometric to the region here. So basically what you can do is you can conjoin the region 3 and 3 prime together. And by doing this, you get a new Kruskal diagram, right? You get a Kruskal diagram where this region here is connected to this region here. So you would think that there are only two, this is the minor subtlety, right? In the Schwarzschild case, we only have one Kruskal diagram because in the Schwarzschild case we only have one event horizon, but in the Reissner-Nordström case we have 2 event horizons. So you think that, oh, it makes sense that there are 2 Kruskal diagrams, but actually there is a minor subtlety, is that we can introduce new coordinates, namely u plus prime and v plus prime, and analytically continue this to give a new set of regions, 1 prime, 2 prime, and 3 prime. And through iteration, we can get an infinite Kruskal diagram. So let me mention before, I obtained this figure from Rial's lecture notes on page 89, and this one on the same page, page 89. So you can see we get a new u plus and v plus coordinate that can be conjoined again to the 3 prime region here. So by introducing a new set of Kruskal coordinates, we get a new asymptotically flat region. And through iteration, we get an infinite Kruskal diagram, which is quite interesting. Now, recall that the caveat to Kruskal-Szekeres coordinates is that we need an infinite coordinate chart to describe the physical features at asymptotic infinity. For example, future and past space-like, time-like, and null infinity, which I guess it's all right if you're thinking about it, but if you want to summarize them all in one diagram, it is better to have a finite coordinate chart. So as we learned in lecture 3, we can map the infinite regions to a finite one using conformal transformations using Penrose coordinates. So the Penrose coordinates is basically we take the arctangent of the u plus and minus and v plus and minus coordinates respectively. And we can see from the equation above that mapping these basically u plus and v plus and minus to minus infinity and plus infinity respectively, we get a map of u tilde and v tilde in the minus pi and pi regions respectively. So you can map an infinite region to that of a finite one. And moreover, when we set u plus and minus and v plus and minus to 0, we also get u tilde plus and minus and v tilde plus and minus to 0. So what happens is you would think that sometimes the 0 coordinate may yield a singularity, but in this case it does not. So which means that the lines that correspond to the event horizon remains at 45-degree angles. So in short, what you can do is you can draw a Penrose-Carter diagram like I showed in my previous lectures. And what happens is, I mentioned before, for example here, you can conjoin the region 3' and 3 together. And you can also conjoin this 3' to this, or maybe 2' to this 2' here together. So what happens is when you do this on a Penrose, because in the previous case, you would need to conjoin infinite regions of infinite coordinate chart. In the Penrose-Carter diagram, you can conjoin the regions of finite coordinate chart, and you can summarize them in one Kruskal diagram. And you can see that, as I mentioned before, the region 3' is so this one was the original what do we call it? This was the original Kruskal diagram. And what we can do is we can conjoin it to the one with the curvature singularities at r equals 0. And what happens is you can also, by introducing a new set of coordinates, you can also conjoin it to another region that is isometric to the original u plus and v plus ones. And then you can also further analytically continue it by introducing a new set of u minus and v minus coordinates, and then you get a new Kruskal diagram. So this is an infinite iteration of Kruskal diagrams, and then we can summarize them in one Penrose-Carter diagram using conformal transformations. So this is quite nice, and I obtained this figure from again Rial's lecture notes, page 91. So after drawing Penrose-Carter diagrams, so let us have a brief discussion on Cauchy horizons. So let me define what a Cauchy horizon is. For a manifold described by M, let I plus or minus be the set of points confined within the future and past light cone, and let sigma be some Cauchy hypersurface. So I probably have not defined a Cauchy hypersurface before, but essentially what a Cauchy hypersurface is a hypersurface that is achronal. So what does that mean? When a hypersurface is achronal, this means that a world line that connects, so basically if we have an event in space-time, we can represent it by a world line. And a Cauchy hypersurface is a hypersurface that intersects the world line only once. This means that this represents an event happening at one instance of time and space. So this kind of means that you cannot, this I guess precludes any closed time-like curves, and it precludes any things like going back in time. So if you have a world line that does this, and you have a hypersurface that cuts the world line, it intersects the hypersurface twice, and this is not a Cauchy hypersurface. So a Cauchy hypersurface is one that when we have one world line, the hypersurface only intersects the world line once. And now let us define d plus or minus as the future and past domain of dependence, and that is the set of points within M such that the past or future in extendable causal curve intersect P and sigma at the P and sigma simultaneously. So then the future or past Cauchy horizons can be represented by the following. So it can be represented by the following equation, and it is basically so this overbar represents the closure of the set, and by defining in this matter, so basically it is the closure of d plus or minus and excluding the points within the past or future light cones within this domain of dependence. And the total domain of dependence can be thought of as the union between the past and future domain of dependence. So for those who are a little bit more geometrically minded, we can also think of the domain of dependence as the following. So if we draw a space-time diagram of Minkowski space, the green region represents the future domain of dependence, and the red, the blue region represents the past domain of dependence. And again, I obtained this figure from Rial's lecture notes on page 34. So if sigma is geodesically complete and asymptotically flat, so let me explain what I will define geodesically complete later when I talk about singularity theorems, but geodesically complete essentially means that there is no point on the space-time manifold where you cannot continue a null geodesic indefinitely. So basically, with singularities, if something is geodesically incomplete, you can have a point where you cannot continue a null geodesic indefinitely, and this is called null geodesically incomplete. But this manifold we assume is geodesically complete. Not a manifold, sorry. The hypersurface is geodesically complete, and by asymptotic flatness, we already kind of know what that is, but I will define it in more detail later when I talk about singularity theorems and positive energy theorems. So the Cauchy hypersurface, as shown by the Penrose-Carter diagrams, is described by the previous figure. So so here, and it is important to note that d plus or minus is bounded by the future past Cauchy horizons, and both the future and past Cauchy horizons are at r minus equals 0. And thus the existence of these Cauchy horizons implies that the regions apart from the domain of dependence are unphysical. And this is because the regions that correspond to the domain of dependence are uniquely determined by the initial conditions, basically the initial datum on sigma. And this is a consequence of a proof by Choquette-Bruhat and Garrosh that showed that the Einstein equations are a well-posed initial value problem. And subsequently, this is shown, well, the word unique is further exemplified by Carter and Robinson's uniqueness theorems for black holes. So the regions outside these d of sigma are not determined by the initial datum, but determined by analyticity and spherical symmetry. So if we assume that sigma is smooth, then our analytically if we assume that sigma is smooth, then our analytic extension of d sigma is not unique, meaning that there are infinitely many ways to do so. Hence, this extendability seems to violate a well-known conjecture in general relativity known as the strong cosmic censorship conjecture. And I will talk about what this is. So the strong cosmic censorship conjecture is for a Cauchy hypersurface. So basically, with an initial datum defined by the Cauchy hypersurface, the first fundamental form, and the second fundamental form, let this initial data, and given that this initial datum is geodesically complete, asymptotically flat, and satisfies the vacuum Einstein-Maxwell equation, then generically, the maximal Cauchy development of this initial datum is inextendable. You may think that this violates the strong cosmic censorship conjecture, but remember, the cosmic censorship conjecture uses the word generically, and the key word here is, this is the key word, because the violation of the cosmic censorship conjecture is only valid, basically a violation of this conjecture necessitates that d sigma is inextendable for a sufficiently small perturbation of the initial datum on sigma. The reason why this does not violate the strong cosmic censorship conjecture is that the perturbation could be sufficiently large such that it breaks spherical symmetry, or alternatively, it could preserve spherical symmetry, but introduce matter into the system. And there is strong evidence to support this, as a paper by De Fermos proved that one can lead to spacetimes where the Cauchy horizon can be replaced by null curvature singularities, given that the perturbations of the initial datum on sigma are sufficiently small. And this is written in his paper in 2014 on a paper called Black Holes Without Space-like Singularities, and it's in the Mathematical Communications in Mathematical Physics. So this is a peer-reviewed paper. This implies that the strong cosmic censorship conjecture is respected for spherical symmetric initial datum on sigma, and the singularities from charged black holes formed by spherically symmetric gravitational collapse of charged matter. Basically, let me rephrase that. So basically, the singularities from a charged black holes formed by a spherically symmetric collapse of charged matter will either be partially space-like or null. However, it is important to note that this model is highly restrictive, as they only consider a spherically symmetric solution to the Einstein-Maxwell equations coupled to massless scalar fields. I mean, if you invoke something like massive scalar fields and etc., this could not be true. So in general, a rigorous proof for both the weak and strong cosmic censorship conjecture remains an open problem in mathematical general relativity and differential geometry. And but the key thing to note is that about Cauchy horizons is that we should not, looking at this Penrose diagram, we should only consider the regions that are defined by d sigma. So basically the domain of dependence and the initial datum. So basically, in principle, you should only take the regions 1, 2, 3, 4, and this region seriously, because the other regions are essentially non-physical, or sorry, are essentially unphysical, because they are obtained through analytic continuation and a spherical symmetry. But this way of analytic continuing the Penrose diagram is not unique, and basically we can essentially say this is not physical. So that concludes what I have to say for this lecture. And in the next lecture, I will talk about different things. I will talk a little bit more about stable orbits stable orbits around charged black holes. And in this lecture, I will, I guess, apologize in some sense because there's no novelty. And in the next lecture, I will introduce some novelty because I will be illustrating what a stable orbit is in the context of phase portraits. So I hope you look forward to that, and I hope you learn something from this lecture, and see you in the next one. Thank you.